Here's lesson 119 number 8. We already did 119 number 6. 119 number 8 wants the positive real roots of this polynomial. So I'm going to use Descartes' rule of signs. So I'm going to look at the sign of each of the terms and determine whether I'm going to say yes if there's a change and no if there's not. I went from positive to negative, so I'm going to say yes, there's a change. Negative to negative, no. Negative to positive, yes. Negative to negative, positive to negative. There's a yes and a yes. So how many sign changes? 1, 2, 3, 4. So if there's 4 sign changes, then there could be 4 or 2 or 0 real positive roots. So why do we skip down by 2 each time? Because the imaginary roots could come in, they always come in pairs. So if there's a non-real or a complex root, there's not just going to be one, there's going to be 2 of them. That's why we're skipping by 2 each time. And why does the sign change, why do we care about that? I think it has something to do with, this is a quintic. Sign changes, like over here it would be positive, like the y values are positive, and then as soon as there's a root, then the sign changes to be negative, right? And then positive, then negative, then positive. It has something to do with that. If you're looking for negative real roots, then you plug in negative x for each one. So plugging in a negative for x right here, and my power being odd, I would actually, this term would turn into a negative 6x to the 5th. And it's kind of the same. The video that I did right before this one has an example of looking for negative real roots. But when you look for positive real roots, like they just asked us to, you just take the polynomial as it's written and just check the signs of the terms, count the sign changes, then subtract 2 from the sign changes. Like there could be 4 or 2 or 0. Okay, so there's part I didn't talk about that's in lesson 119, and that's upper and lower bound theorem. So there's a way to find, now we already found region of interest. Region of interest, you look at the polynomial and you find the largest coefficient, and then you take the absolute value of it and add 1. So this one, the region of interest, would be 35 plus 1 is 36. Well, that's a pretty darn big circle for this thing. I mean, you can see that you do need the 36 because it goes up that high. But, I mean, that doesn't tell you much if we have a giant circle. So there's another way to find out where the interesting parts of a graph occur. You can find the upper and lower bounds. Okay, so, and it says, it says a little bit about it, but basically what you do is if you want the upper bound, you're going to pick any nice integers like 1, 2, 3. I usually start at 1, and then I try 2, then I try 3. Sometimes I'll skip if I feel like I'm, well, once you start doing them, you'll see that you're going to have to pick a bigger number, but I'll start with 1, and then I'll try 2, then I'll try 3. For my upper bound. Those are positive integers. So I would try synthetic division with 1 as a divisor. If that didn't work, I'd try 2. Now, how do I know if it worked or not? When all of these numbers down here on the bottom, when they're all the same sign, then I know I found my upper bound. So in this case, they tried 1, and they had like positive numbers and negative numbers down here. Because these are the coefficients of the degree that's 1 lower than what you started with. So that kind of makes sense because these are terms of a, what was this thing? These are terms of a quartic. If you started with you started with a quartic, so these would be terms of a cubic. Anyway, when you get all the bottom row and they're all the same sign, they're either all negative or all positive, then that's your, whatever you divide it by, that's your upper bound. Then you do the same exact thing but use negative integers. So try dividing -1, -2, they skipped the -2, -3, -4. And then on the negative, when you're trying to find the lower bound, you want alternation. You want it to go positive, negative, oop, that one's not positive, so that's no good. You want it to go positive, negative, that one's no good. Positive, negative, positive, negative, positive. It alternates. So this means that negative 4 is your lower bound on that polynomial. I'm going to do one for you. I'm going to do number 119. 119, number 10. So it's a cubic, and I'm going to use some synthetic division. So for the upper bound, I'm going to try 1. So the coefficients would be 1, and then I'm missing the x squared term, so I put a 0 in there, and then I put the negative 3 and the 19. So I try positive 1 because I'm looking for an upper bound, and my sign, right here, my sign isn't the same as the other two, so I just give up immediately. I don't want to waste time. So then I try 2. Divide 2 into it. Oh, I got positive, 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 positive. So the upper bound must be 2, because these are all the same sign down here. Okay, lower bound. I'm going to try dividing negative integers into doing my synthetic division. So I want it to go positive, negative, positive, negative, positive. I quit right here because I got positive, negative. I see when I do that, that's going to be a negative, so I just gave up, went to the next one. Positive, negative, positive. Wait, what? Positive, negative. This thing right here would have been positive, but that's also positive. So I gave up on that one. And I know I ran out of room. I tried negative 3, positive, negative, positive. I see that's still positive, so that's no good. So I try negative 4. Positive, negative, positive. I don't even care what that number is. I just know that 19 minus 52 is going to give me a negative, so I know negative 4 is my lower bound. Okay, now what else is there in our chapter? I think there's no more problems, but we're supposed to talk about irrational roots. So we talked about finding complex positive, or we talked about finding positive roots and negative roots and combinations of real roots and complex roots, but we never talked about rational roots. Irrational roots. We have the rational root theorem can give us rational roots, but we don't have anything for irrational roots. So that's kind of what this is saying right here. So it's, we know that there's going to be some 0. If you see a sign change from the y, see how like my y value right here is a positive 0.5 and then a negative number. We know that if the polynomial changed from being positive to negative, we know it must have crossed the x-axis at some point. But the book right down here, it says, the procedure used in the past for finding irrational roots required paper and pencil calculations. It basically says we can do this with a graphing calculator. So they're just telling you that for your information. But right now you're just supposed to be using Descartes rule of signs. You have your rational root theorem. You have your upper and lower bound theorem. So all these ways of finding roots of polynomials.